Hello and welcome. This week we will continue our discussion about global change, climate change, and greenhouse gases. We'll also talk a little bit more about thermohaline circulation, and we're going to look at the unequal heating effects that we see in different areas. We'll also be looking at how effects in the Arctic can have long-reaching and sweeping effects on the planet. There are natural cycles that we've already discussed which affect surface temperatures, and we know that some of those have to do with solar radiation, the sun's magnetic field, changes in the axes and the ellipses of our orbit, so a lot of planetary level stuff. And we know that when we look at the geologic record, we had seen these spikes in temperature, right? So we had seen that there were interglacial maximums, and then there were the glacial periods where you had much cooler temperatures and things like that. What we saw is that in no time did carbon dioxide ever go above 280 parts per million. And so we are now way above that. We know that temperature seems to be modeling that based on increased greenhouse gases in the atmosphere. So going back to looking at Earth's temperature now, when we zoom in here and look at Earth's temperature over some different time periods, we can again see, and this is on a scale that is measured from, they use 1961 to 1990 kind of as an average, and then they put everything else on the scale in reference to that, okay? So you can see that it was on the scale much cooler globally than it obviously is today. And so we're seeing this overall temperature increase, and there's this really cool animation that I will show you in a minute here, where we can look at the variations country per country. So when we think about heating, the heating we find is not always equal. And so there's a lot of different temperature anomaly figures that look like this that you can find online at any time. Just type in global temperature anomalies and they'll show you different spottiness. And so what you'll see is that at different times of the year you'll have different hotter periods, hotter bands, cooler bands, things like that. You can also look at temperature anomalies, and if you look during the summers, one of the things you'll see is that typically we have a lot warmer temperatures in polar regions than we're used to seeing. So again, that's contributing to the melting of ice caps, glaciers, and all those types of things. We also definitely still see some areas where you have quite a bit of heating that are even much more southern or tropical, and it's not even, right? So we don't see an equal distribution of everywhere gets warmer. We actually see that there are some areas that get cooler, right? So ask anybody who lives in the Hudson Bay region on the East Coast or even in Newfoundland, and they'll tell you that their summers have not been getting much warmer. And again, that's just due to these spatial differences and all of these different components. And again, mountain ranges and things like that can have major effects on those, on the heating and basic distribution of water and all those other effects. So now if we go to this animation and we look at, let's start this here and talk over it for you, what we can see is that we've got these fluctuations here. And so we have the clock counting up, and we've got all these different countries around the outside. And so what you can see is that as these times get more orange, more red, we're seeing much greater temperatures. And so you can see that initially when we started, everything was more in the blues and yellows. And now as we're approaching this one ends at 2016, we're seeing much redder versions. And so we know that these temperature anomalies, the divergence from the temperatures of the 1960s are really quite drastic and are affecting a lot of areas and affecting areas unequally. Right? But what we do see is that every area is affected. There's nobody on here that's blue in 2016. But there are some areas, so we've got here, we've got here, so we've got Afghanistan there, we've got Canada here, just seeing a lot warmer temperatures. We've got, can't quite tell who those folks are, Turkmenistan, Uzbekistan, all those folks seeing much more higher temperatures. Again, a lot of it tends to be northern latitude areas that are seeing these drastic increases in temperature. All right, so obviously in a warming world, these spatial differences are relatively evident, And I challenge you to go out and to look at all of the different data out there. It's pretty amazing the amount of data that has been compiled globally to make some of these really cool images and for us to be able to understand exactly what's happening on a global scale. So when we talk about this uneven heating and these challenges that we're seeing in heating at the globe level, one of the things that we're seeing is that because we have increased heating in areas in the Arctic and things like that, this is leading to much more melting of sea ice, much more melting of land ice. The melting of sea ice doesn't affect overall sea level, but the melting of land ice does. The melting of both actually has effects on that conveyor belt we were talking about before, because you have more fresh water, which is lighter in these Arctic regions, which then limits the subduction of the North Atlantic deep water. The other thing, though, is it's somewhat of a positive feedback system. So remember how we talked about albedo? Albedo, so you'd have a lot more solar radiation bouncing off of these white surfaces and returning to space than you would as they melt. And so you end up with this positive feedback where once things start melting, the melting process tends to be speeding up year after year after year. And so there's areas in the Arctic now where it's like, this is the third year that we've seen no sea ice in the summer, the fourth year, and so on and so forth. And we have the ability also to measure from space the thickness of sea ice, and so you can see really clearly that from the 1950s to what's projected in 2050 is projected that there will probably be very little sea ice left. Now, obviously, this has a lot of consequences for everybody on Earth due to thermohaline circulation, weather patterns, sea level rise, and all these components, but it also has some warm, fuzzy issues as well. So a lot of folks have heard about the plight of the polar bears. Polar bears don't have as much sea ice, so they're swimming drastic differences, and a lot of them are dying from starvation because they just can't find food and hunt as they used to. So there's the warm, fuzzy angle as well. Here's another graph that shows the average monthly Arctic sea ice and giving you an idea, and this is summer, so this is when it would usually be the most melted. So we're looking at August here, and if you look along this curve, what you see is a general downward trend. And I don't have more recent data for this, but I can tell you that it has not improved. And what would happen if the Arctic were ice-free? Well, we'd have these continued issues with less albedo, right? We'd have more radiation being absorbed. It would then allow more heating and even a stronger temperature anomaly to occur in Arctic areas, right? And as we decrease that albedo, we're absorbing more energy onto Earth, and again, everything turns into a positive feedback system. There's the warm fuzzy angle I just mentioned when we were looking at the Arctic melting and polar bear habitat. You may or may not have seen that Discovery Channel show where they're looking at polar bears in this region here that actually are now hunting baby whales from rocks because it's actually easier for them than trying to find sea ice to hunt from. And as I mentioned, decreased sea ice is bad, but actually decreased land ice is much, much worse. And there's many reasons for that. One is that this albedo piece. So when land ice melts, we have usually typically rocks underneath. A lot of them end up being like volcanic rocks or granite and things like that, all of which tend to be darker in color and absorb more heat, thereby continuing to heat the area even more. Also, not having as much of a surface for great albedo leads to less albedo. The melting land ice also increases the overall ocean volume and therefore contributes to sea level rise. And then again, when we have this melting of all this fresh water in these northern Arctic areas, it's contributing more fresh water to these systems, which is leading to disruptions in that North Atlantic deep water subduction zone. Okay, and so here's a little bit of a graph just to show you the overall shrinking of the land ice on Greenland. Here's a beautiful shot of a glacier melting on Greenland. The other thing that we haven't talked about a lot is subsidence. So one of the things that we have happening is when you have these huge ice sheets on land, the land actually kind of gets pushed down. As the ice melts, the land kind of rebounds because there's less weight on it, also causes major earthquakes and other challenges for these areas as well. I grabbed this image though to show you because I wanted to talk a little bit about how land ice actually can really disappear on a very quick scale. So once you get water starting to pool and water heats up more and more, it typically forms like cracks or fissures within the ice sheet, and water then penetrates down. And so once it penetrates down to the bedrock level, it basically creates this nice slippery surface. If anybody can think about sliding an ice cube across a desk. If you grab an ice cube out of the freezer and put it on a desk and go to slide it, it slides really well. You wait a minute or two until it's even a little bit more melted, and whew, it just flies across that flat surface. So that's exactly what we see happening with ice sheets. As soon as they have this liquefied bottom layer, and we have this whole half here that's kind of cutting down, we can have what we call calving of these ice sheets. So just huge amounts that just break off and then flow into the ocean. And as we mentioned, these can have huge effects on this thermohaline circulation. Here's Greenland with all this melting land ice going into this area, lots of freshwater intrusion, and messing with the overall AMOC, or the North Atlantic Deepwater Subduction Zone. There was actually a movie made about this. You may or may not have seen it, The Day After Tomorrow. And in that movie, it was like the whole conveyor belt screeched to a halt. And when it did so, it was this impending winter was coming everywhere, and the winter was chasing people, and it was, a very dramatic movie. Obviously, what would happen in real life is not as dramatic, but in the long term, we very much could have really significant changes in the movement of waters, which would have really significant changes on weather. So, for example, for us, we would end up with potentially really, really cold conditions because the northern air would penetrate a lot farther south than it currently does because we wouldn't have warm air currents sort of pushing it off. One of the other big things that we haven't talked about yet is methane and methane releases due to increasing temperatures. So we talked about methane in the last lecture about being a greenhouse gas that has a higher warming potential than carbon dioxide. But the other thing we haven't talked about is what leads to increasing releases of methane. Obviously, the use of or the release of natural gas would cause more methane in the atmosphere. But what actually is the biggest concern is the melting Arctic. So what we have is we have the permafrost, we have other Arctic lakes and things like that that have old organic matter in them, sat there for a long time, usually in anoxic conditions, and decomposed. In doing so, it produced a lot of gas, but all those gases were frozen and trapped beneath these layers and layers of ice sheets, as well as permafrost. So as the permafrost starts to melt, all of this gas is starting to be released. In Arctic areas already, it's causing major issues. Here's a railroad track that used to be straight, and as you have the permafrost melt unevenly, causes some challenges there. Here's a cut in the side of a hill where you can see, yep, you've got soil on top, but then you've got all this permafrost underneath. So significant amounts of permafrost that once that starts to melt can release the gases back into the atmosphere. Globally, permafrost affects all of these areas. So there's a lot of area that is melting and leading to increases in gas release. Now, there's actually been some interesting political or geopolitical components to this. So Canada, for example, sold off a lot of its Arctic areas that with permafrost for mineral extraction purposes, meaning that, and it was China that purchased it, they have the ability to create systems to extract these gases from these systems to use for their own natural gas purposes, which is kind of interesting. This slide is nice because it shows you a little bit about the different components that contribute to methane gas release. So you've got the permafrost piece, but then you've also got, volcanoes can contribute, gas hydrates, frozen gas hydrates, different faults, and all these types of things that can contribute to the release of methane or natural gas back to the atmosphere. In the United States, there's a lot of what's called fracking that is done. So that's fractionation is what fracking is short for. And they create many different microfractures. They stick a pipe down there, they flush it with water, create lots of microfractures using chemicals and pressure. And when they do so, any of the gases in those shale components can start to percolate out. And so then they capture those gases and then use those to give us the natural gas that we use to heat our homes and things like that. When we look in the Arctic, again, there's like these methane seeps that we're seeing from Arctic seabeds, permafrost melting areas, and all of that. I'll actually show you a video right now of an Arctic lake where the methane that is melting is still trapped beneath the surface.
Is here because the permafrost is thawing, and when it thaws, there are microbes in the bottom of the lake that eat the carbon that was in the permafrost, and they make methane gas. One molecule of methane is like 25 molecules of carbon dioxide, so it's a really strong greenhouse gas. And methane is contributing to climate warming and making the warming that's already happening worse. So get down low.
Okay.
And as soon as I put this in, as soon as I break through, gas will rush out, and you want to basically get it right down
right
into
above
the gas
the hole.
stream.
Okay.
Ready? Boy! Holy crap.
So that's a rather hilarious video where the person who's supposed to be the expert in showing you that methane can be released from these lakes actually gets a huge amount of gas coming out in their direction, causing them to actually get burned by it. That full video is actually part of your assigned videos for the week, so you'll have a chance to watch that entire video. So one of the other problems that we see with permafrost is from an infrastructure perspective. We see a lot of areas where pipelines, streets, roads, houses, all of these types of things, as the permafrost melts, the land collapses, and we end up with major significant challenges. So it's a big challenge for Arctic areas. Anyhow, as we add this all together, all these different components that we've talked about this week, and we look at carbon dioxide, methane, a little bit of nitrous oxide, and all of these other components, there's a lot of interactive effects, and a lot of these effects have actual positive feedbacks on this global change or global warming system, which make things even more difficult for us to be able to basically catch this runaway train once it runs away too far. So some of these positive feedbacks, obviously, as ice melts, more heat is absorbed, leading to more ice melting. As the oceans warm, more CO2 and methane is released, which results in more warming, which results in more methane and CO2 release. The melting permafrost also releases more methane, which leads to more warming, and the same positive feedback cycle. And oceans warm. They also acidify as carbon dioxide gets absorbed into them. We'll talk about that later in the course, and kill marine life. And with forests, as more forests dry out due to changes in precipitation patterns, we end up with more fires, more dying ecosystems. When they die, they decompose and put more carbon dioxide back into the atmosphere. So there's a lot of really nasty negative feedback, positive feedbacks that really start to happen as we change the climate system. And so one of our big challenges is making sure that we don't have these sweeping changes. Thanks so much, and I'll see you next week.